Okay, in today's lecture, we're going to finish the section 5.3 material on the integral test. So in the second half of this material, we're going to be evaluating or trying to approximate the sum of a convergent series. So far, there are only two types of series which we're able to find the sum of if they converge. And those two types are telescoping or geometric series. We had a way to find the sum of those series if they converge. But most other series that we work with in this course, we can determine whether they converge or diverge, but if they're convergent, we may not be able to find the sum exactly. But we could approximate it. So that's going to be our problem of interest for today's lecture. So let's suppose that we have some series of terms a sub n, and we know that it is convergent. So it converges to some sum, and the sum of that series let's call capital S. Now let's suppose that we want to approximate the sum of that series. If it's not telescoping and it's not geometric, then we don't know how to find the sum, but maybe we can approximate it. So let's think about how to approximate it. Now, since our sum S is defined as the limit of the sequence of partial sums, that is, if we take the nth partial sum S sub n and allow n to approach infinity, that's how we defined the sum of our series. So we could use the nth partial sum as an approximation of the sum, and it should be a good approximation as long as n is sufficiently large. So if I wanted the sum of my series, maybe I could look at the sum of, say, the first 10 terms, the first 100 terms, the first 1,000 terms, and use those partial sums as an approximation of the sum of the series. But the question is, well, how many terms do you need to get a good approximation? So how large is sufficiently large here? Is the first 10 terms enough, or do we need the first 1,000 or million terms? So to answer that question, let's introduce a little terminology. We will define the remainder in using the nth partial sum, S sub n, to approximate the sum S of a convergent series as follows. So it's denoted as capital R sub n, the remainder in the nth partial sum approximation, and it's the difference in the value of the sum of our series S and the nth partial sum approximation. It's basically how far our approximation is off from the true sum S. Now, since S sub n is the nth partial sum, this difference would just be the sum of the terms starting at n plus 1 out to infinity of the terms of our series A sub I. So this remainder gives us some estimate as to how close our nth partial sum approximation is to the true sum of our series S. Now we have a theorem regarding this remainder, which will allow us to determine how many terms we need to add for a desired accuracy. And this theorem is what is called the remainder estimate for the integral test. So we know that for certain series, we could use the integral test to determine convergence. So examples would be P series or series that we saw in the first part of this lecture. So let's suppose that we have some series of terms A sub n, which we are guaranteed is convergent by the integral test. And let's define R sub n as the remainder in the nth partial sum approximation. So this theorem says that remainder in our nth partial sum approximation is bounded below by the improper integral of the function f of x from n plus 1 to infinity, and it's bounded above by the improper integral of f of x from n to infinity. So for this theorem, really the inequality that we care most about is this second one, finding an upper bound for the remainder in our approximation. So let's see how we could make use of this remainder estimate to approximate the sum of a convergent series. So in this next example, we are asked to consider the p-series, sum from 1 to infinity of 1 over n squared. And let's first ask ourselves if that series converges. So in this case, the value of p is 2, this power here, which is greater than 1. So we know that this series converges by the p-series test, since the power p in this example is equal to 2, which is greater than 1. So I know it converges with a sum that we're going to call capital S, but since this series is not geometric and it's not telescoping, we don't know how to actually find the sum. So in part A of this example, we are asked to approximate the sum of that series by using S10, that is the 10th partial sum, or the sum of the first 10 terms of that series. So here, let's denote by capital S the sum of this series from 1 to infinity of 1 over n squared. So to approximate S, I could use the 10th partial sum, S sub 10, which would be the sum of the first 10 terms. So let's write them out here. Starting with the first term, n equals 1, we have 1 over 1 squared, which is 1, plus for the next term, we would have 1 over 2 squared, so 1/4, then 1 over 3 squared, 1/9, 1 over 4 squared is 1/16, and so on, until I get to the 10th term. When n is equal to 10, we have 1 over 10 squared, or 1/100th. So this sum of the first 10 terms would be an approximation of the true sum of this series. Now we might ask, okay, if we're using that as an approximate value of our sum, how good of an approximation is that? So in part B of this example, we are told to use the remainder estimate for the integral test to determine the error r sub 10 in using this approximation. So we know that R10 is the remainder in using the 10th partial sum approximation to approximate our series. It's the difference between S and S sub 10. So this difference was the error, or how far we're off in our approximation from the true value of our sum. So by the remainder estimate, for the integral test, we know that the remainder, r sub n, or in this case r sub 10, is less than or equal to the improper integral from n, so in this case n is equal to 10, out to infinity, of the function which defines the terms of my series. So here we were working with the p-series 1 over n squared, so our function is 1 over x squared dx. Now to evaluate this improper integral, we have to make use of a limit. So we would take the limit as some variable t approaches infinity of the integral from 10 to t of 1 over x squared dx. And our antiderivative of 1 over x squared is negative 1 over x to the first power, where we're evaluating from 10 to t. So we have the limit as t approaches infinity of negative 1 over t minus a negative, so plus 1 over 10. So as t approaches infinity, this first term, 1 over t, will approach 0, and we're left with the limit of a constant 1/10, which would be 1/10. So this remainder estimate has told us that the error in our 10th partial sum approximation, that is the approximation that we were using in part A, is less than or equal to 1/10, or 0.1. So I know that the approximate value I found in part A is within 1/10 of the true value of my sum. So here we could say something like the error in using S10 as an approximation is at most 1/10. So we have some way to determine how accurate our approximation is. We know it's accurate to within 1 decimal place here, since we have an error of at most 1/10 or 0.1. So let's look at another example that sort of works in the opposite direction of this one. So here, let's consider the p-series sum from 1 to infinity of 1 over n to the 4th. So we know that this converges because our power p is greater than 1. So we could make a little note to the side here. We know that this series will converge by the p-series test, since the power p is equal to 4, which is greater than 1. So we know that this infinite series has a sum, which we're going to call S. And if we want to approximate it, we could use the sum of the first so many terms. So in this example, the question is, well, how many terms do we need to add to get a desired accuracy? So here we are told to use the remainder estimate for the integral test to find the value of n such that the error in the approximation using the nth partial sum is less than 0.01 or 1/100th. So that is, how many terms do we need to add to ensure accuracy to within 2 decimal places, or so that our error is less than 1/100th. So here, again, let's use capital S to denote the sum of this series, 1 over n to the 4th from 1 to infinity. So we could denote as R sub n the error in using the nth partial sum approximation for the true sum of this series. Now we know by the remainder estimate for the integral test, this error, R sub n, is bounded above by the integral from n to infinity of our function, in this case 1 over x to the 4th dx. So to evaluate this improper integral, we use a limit. We would take the limit as n approaches infinity, let me use a different variable. Instead of n, let's use, as t is approaching infinity, the integral from n to t of 1 over x to the fourth, or x to the negative fourth dx. So we have the limit as t approaches infinity of, for our antiderivative, we'd have x to the negative third divided by negative 3, or negative 1 over 3 x cubed, which we're evaluating from n to t. So that gives us the limit as t approaches infinity of negative 1 over 3t cubed minus a negative, so plus 1 over 3 n cubed. And as t approaches infinity, this first term, 1 over 3t cubed, will approach 0. So we're left with just a 1 over 3 n cubed. So what we found so far is an expression for the maximum value of our error. The error in our approximation using the nth partial sum is less than or equal to, so it is at most this value, 1 over 3 n cubed. Now, if we want to have an error in the problem, it said less than 1/100th, we could take this expression that we just found for the maximum error and make sure it's less than 1/100th. So here, let's say the following. To ensure the desired accuracy, we're going to let this maximum error, 1 over 3 n cubed, be less than 1 over 100th, since we needed our error less than 0.01 or 1/100th. So what that means, if I were to cross multiply here, I need 100 to be less than 3 n cubed, or 100 over 3 to be less than n cubed. So now the question is, well, what would be the smallest value of n that would satisfy this inequality? So to answer that question, well, we could start by choosing values of n and seeing what's the smallest value that would satisfy this inequality. So if n equals 1, we would have 1 cubed, which is not greater than 100 thirds. Our 100 thirds is 33.3 repeating. So let's try the next integer value. If n equals 2, we would have 2 cubed is 8, so 2 doesn't work. If n is 3, we have 3 cubed, or 27, which still isn't greater than our 33.3. But if n is 4, 4 cubed would give us the desired accuracy. So we would have 16 times 4, which is indeed greater than our 33.3. So here we need the value of n to be at least 4. That is, I need to add at least the first 4 terms of my series to get accuracy to within 2 decimal places, or with an error of 1/100th at most. So here, n greater than or equal to 4 is the condition that we need on n in order to ensure the error in our partial sum approximation has our desired accuracy. Now, once we have found that, in the next part of this problem, we are asked to approximate the value for the sum of that series to within 1/100th. So by what we found in part A, the sum of our series, n equals 1 to infinity of 1 over n to the fourth, which we were calling s, could be approximated by using the fourth partial sum, or larger values for n, something larger than 4, but 4 at minimum. So here, the sum of our series is approximately the sum of the first four terms. So starting with n equals 1, we have 1, plus, when n is 2, we have 1 over 2 to the fourth, so 1/16, plus 1 over 3 to the fourth is 1 over 81, and then plus 1 over 4 to the fourth, or 16 squared, which is 256. So this expression would be an approximation for the sum of that series, which is accurate to within 2 decimal places, or to within 1/100th.